Perfect. Welcome everyone. This is, I believe, the third CITP seminar of the semester. And it's my great pleasure to welcome and to introduce Professor Pramod Viswanath. Pramod is currently the Forrest G. Hamrick Professor in the EC department. And prior to joining Princeton, Pramod was a faculty member at Illinois. So we are really thrilled that we were able to see Pramod away from Illinois. Pramod's background is actually really interesting. He, I think, was trained as an information theorist at Stanford, which you can't tell at all from his at Berkeley. Okay, sorry about that. At Berkeley, which you can't tell at all from his current website because all of his current interests and passions are centered around blockchain technologies and topics pertaining to Web 3.0. But some of his very early contributions in research were around information theory. He wrote, I think, one of the foundational textbooks on wireless communications as well. He's also a co-founder of a blockchain startup called Kaleidoscope. And really excited to have you here at CITP. Looking forward to it.
Thank you, Pratik. Thanks all for coming. I'm excited to be here. And it's also the first time I'm giving this talk, so I'm quite, especially excited about it. So there may be some kinks. Let's talk about it. Pratik mentioned I have some background in wireless. I do blockchains, and this talk is, old flame meets new flame. It's like it's a combination of years of actually decades of my career together. I enjoy building information systems, things that especially scale globally, man, woman, child. So that's a common theme in my activities. And then trying to spend the blockchains of it. So this talk is a mix of both. Okay. So I'll start with the wireless side and the networking side. There was a vision that there would be a communication fabric that people pitch in links, people pitch in computing and sockets, and that would link together the world. And it was Web 1.0, the vision of the internet. And for a large part, there were some servers and portals in the late 90s when I was a grad student. And then, but still the underlying network and the core, there were a few players, but largely decentralized. And so the Web 1.0. As the decade rolled by and the information age settled in even more sharply, centralizing forces. And I'm but this is a CITP, and I'm sure there are experts who can shed more light on why this centralization happened. But there's no doubt that it has happened. And it will be a combination of technological, economic, autocratic forces, largely centralized. This is the Web 2.0 that we live in, and I'll just say, we can look at centralization in so many ways. This is just a market cap I pulled down this month, and you'll see that I only put down a few, but all the top 10, top 20 companies in the world are all what are platform companies. So they're dominant information age, they control content and definitely delivery. Tesla also might think of itself as a platform company. More than a car, I would say. And just a decade ago, this was not the case. I'm looking. This talk was also on that was on purely just platforms, but on the communication fabric, centralization has been even more obvious, and it's ramp. I mean, it's still consolidating. It's still ongoing as of just a couple of years ago. We are down from 4 to 3 carriers in the US, and I mean, there were literally a dozen like late 90s when we were building wireless. And just a few years ago, there were 4, and now we're down to 3. So centralization is very clear, these are the forces. And on the other hand, I want to say that there are tailwinds. Again, and these tailwinds that I'm alluding to are, again, technological tailwinds. That is, the fact that compute has become inexpensive and also very accessible and open. So cloud computing became very commodity compute. Hardware has become very lightweight. So what used to be a base station used to be a large, I mean, I'm of a certain age, so I've seen base stations over the decades, and They used to be of the size of this building all the way down to a large refrigerator. And today it's not even the size of this laptop, just barely a stripped down Linux box with just a radio end, and all the core and everything happens on cloud. So this is the 5G revolution. And Spectrum has opened up, which is not all over the world, but definitely in the US with CBRS, the Citizen Band Radio Service. It's not unlicensed like Wi-Fi, but largely unlicensed, very lightly regulated, I would say. You have to go through a SaaS provider, and FCC will allocate. And for the most part, it's available everywhere in the country, other than some near naval stations around the coast. And the thing that I want to say is that wireless and networking is inherently decentralized. People are everywhere in the globe, so there is decentralization geographically. And there's a reason why carriers, despite the centralization that I was alluding to, this is just US. There is a reason why Google, all the previous platform companies are global brands that I was mentioning here. They're all global brands, whereas these are purely local. Across the border to Mexico and Canada, you won't see them. So they've hit some limits of how centralized they can get. And part of this is inherent to just geography. It's this you can't really, it's just not as easy. And Spectrum, of course, is controlled by different countries. But the tailwinds are blowing for a decentralized revolution. I'll say a little bit about this. Okay, so that is the missing component, and this is the thing that what this talk is about, which is that to stitch them all together, you need a fabric that ties them all together. And I'm going to use the word blockchain to signify this fabric. What would the stitching together imply? Right, that's just the word. What would it imply? What it would imply is that you have a low friction way for people put up base stations. Someone provides compute. There is a quick way to offer spectrum and service and backhaul. So there should be a way to incentivize people to participate in these various network activities, and both on the supply and the consume side. And these incentives should have some low friction way of operating. So there's an appropriate mechanism designed to go with it. Put them all together, I'm going to use this word blockchain. So that's what sort of stitches together. And that's what this talk is the basic building blocks of what such a stitched together fabric would entail. That's what the talk is about. But blockchains are unusual in the sense that I have to first define what they are. I gave you a very concrete feel in that networking context, but that took several words. And so let's say a few more words, but a little bit shorter. And this is the most unusual. I'm teaching a class as well, and first we have to define what we are teaching. And so here's my attempt. Blockchains are 4 words: decentralized, digital trust maybe, platforms. So platform, we've already seen what a platform is. Digital, I think we all can say what we know what it is, as opposed to physical, like a car or a lunch or something physical is different from digital. And but decentralized, we have some idea, and we'll talk, and at least in the wireless context, it's literally geographically separate and so forth. And I guess the only thing is left is trust. And this is how I got into blockchain. So I'm just trying to explain my own drive to work on this topic. Is that trust drives humans as animal species. And there's an anthropologist's word, Harari's words, we are the only animal species that can cooperate flexibly in large numbers. And there are other animals that cooperate in large numbers, like bees and ants and some fish, but very rigid, hierarchical ways. And we really cooperate, and the human societies have organized themselves into structures that promote cooperation, more flexibility, and larger numbers. And used to be the notion of tribal trust. We have the same skin color, we look the same, we even may be related to each other, speak the same language. Religion is a fantastic way to scale. So there's a reason why sort of religion and humanity or biology mix. And but the dominant form of scaling, right? You can have up to 1 billion people scale with religion. But a dominant form of trust and organization of humans are in the I would definitely past the post-World War, Second World War, has been this what I would call an institutional notion of trust. So you can have, and I'm just looking at my case, across the continent, I was in India at the Institute of Science, and there's a piece of paper and someone would scribble something, basically saying I got a degree and I can come across somewhere else and it's accepted. So this is a notion of trust. It scales tremendously, the United States dollar. No one is above the law. So that's a notion of institutional trust. The thing with this, it scales tremendously, but it also centralizes even more. And the centralization leads to corruption and vulnerability to. And this is at all levels. And I was giving the examples of platforms and I was giving networks, but definitely autocracies are part of this same phenomenon.
University
And
administration.
Sorry?
University administration.
Oh, it may be.
Anti-monopoly too.
Okay. I'm on the bottom side, so I'm on deep. So I've never seen the upper ones. But the siren song of blockchains is that you have the scalability of institutional trust without its drawbacks. And I use the word siren song because it's largely an evolving field, both technically. Try to build the underlying, and I'm a plumber by my whole life, so I build the underlying pipes of the information age, and so the pipes are still getting built, and definitely the underlying overlaying economics is being done, and then overlaying the policies and how they work with the rest of society. It's a siren song. So what would the siren song imply? Well, perhaps decentralized Dropbox, decentralized Gmail, eBay, Instagram, where incentives are aligned with consumers and suppliers. So that they have a fair share. So in other words, the more they contribute, appropriately defined more, and the more reward they get, and without a trust middle party. So the cryptographic protocols take care of the trust. The siren song. And what this talk will try to do is to look at the notes and the cadences and the melodies of the siren song in the context of something very specific. Decentralized wireless carrier. Okay, that's the vision and the goal of this project. And this talk is in the early stage. Like I said, the first time I'm giving the talk about this project. Okay. So there is actually such an effort, and it's called Helium, and used to be in the top 100 farms. And they have 1 million hotspots. So this is the thing. It's like a globally recognizable carrier in a way. So it's 1 million hotspots. But what's a hotspot? It's not Wi-Fi. It's not cellular. It's LoRa. So it's unlicensed spectrum, very, very low, lightweight. It's meant for IoT devices, like scooters and so forth. But hardly any data has gone on the Helium network. Hardly anything. Hardly a GB of all ever. But it has 1 million people have put in these hotspots, Helium branded and Helium certified, world over. A lot of them, a good bit of them, half of them in the US, and you can see a lot in Europe and so forth. They're switching to pivoting to 5G because no data happened, and which is true. There's not much IoT data on LoRa happening anyway. So it's there. So how did the Helium get to 1 million hotspots? Part of it is I would say, for salesmanship and inherent human greed of having a token. But the point is that that's I think already brings you an idea, which is that incentives are aligned for people to buy hotspots upfront with fiat, right, cash, and use that to earn tokens. How do you earn tokens? Well, you prove that you're actually covering or providing coverage in a certain area. So Helium has this thing called proof of coverage, which basically their incentive mechanism is that if you provide more coverage than it's already not there, so there are no other Helium hotspots nearby, or you are covering sort of a dark area, then you get more rewards. Roughly, that's the idea of what it is. And correctly done, of course, it should be a digital meritocracy. So you spread the network, you grow the network, and not everybody is crowded in the same place. So you lesser rewards if you put a hotspot and there are already other dozen hotspots nearby. And the Helium has some protocol called proof of coverage, not so much a protocol, it's a few steps, which is anyone wants to put up a hotspot, it sends out beacons, nearby neighbors pick it up and report to a challenger who's sort of outside the network, which has said, you go and say where your location is. Nearby people will say that I heard you, and there's some notion of my hearing. So they all go and report back what they heard. So they'll report the hash of the packet that was sent to a third party, which is a challenger. And presumably this challenger is chosen one out of these million. And they're done in some non-grindable random way. And that's another primitive, but that's sort of separate from this. So you have some notion of picking challengers randomly. They'll pick a witness randomly, and this witness goes and broadcasts. Sorry, not witness. This is the prover has to go and broadcast some beacons. There are witnesses nearby, and they will send that I heard you, but they'll send it to the challenger. And different times, different challengers get sent. Challengers will also have some reward for putting together all the proofs, and of course, the witnesses get the bulk of the reward, and this guy also gets the reward. If you have too many witnesses, then it's a problem, because then that means it's very crowded. If you're too few, that's I mean, if there's nobody, that's an issue too. There's nobody to hear you. You're like out in Mongolia or something, and yeah. But the right spot is a few, and they try to do some incentives around it. So that's Helium's proof of coverage. And security, there are several security researchers here, and you wonder like what's to prevent for me to put two base states. Actually, I never put any hotspot. I just keep it in my basement. I just claim that I have it here. And the witness is also just me. Actually, I can have any number, the right number. And indeed, if you look at Helium's map, there are hotspots in nice hexagonal pattern in the middle of Mongolia, Area 51, demilitarized zones. Obviously, they're not there. And so Helium has a running list of black spots. You have to buy only from us. And so they will do all, they'll do. So it's not a cryptographically secure in any sort of serious way. So it's fairly centralized, and you have a user number, like a serial number, username, password. So it's not so room for improvement. And but it's still the network growth over time is still a fascinating thing. And offline I can share these growths, and Helium doesn't have some. I mean, they also have a bit of data, but you can see how they grew, and there's something good about that mechanism design. Despite despite what I said were deficiencies, there is something correct about some thinking about it, roughly correct. I mean, and the basic idea is that you grow, or you see a global phenomenon, which is 1,000 hotspots spread over the globe by local interactions. That is, I send something and other people around me respond, and the incentives drive more people to grow correctly. And this phenomenon is seen in so many different aspects of the world. In physics, we talk about local interactions. In the physicist model, atomic interactions, and then at the right temperature and the right level of interactions, you see global effects like ferromagnetism. And you have models like spin glasses and icing models, and the underlying percolation or the interacting particle system will sort of explain the global phenomenon. That is sort of physics or natural occurrences. In a little bit more engineering way, you would set up rewards or back off periods in a Wi-Fi protocol, so that if you are, Wi-Fi is, we're all used to Wi-Fi, and the protocol basically is simple. It's just try sending, and if there is a collision, then you back off and try later. How much later is the question? And if you're trying more and more and you keep trying, then you back off more, you further more. So there is a very basic protocol underlying Wi-Fi, and the parameter settings can be explained through the same sort of interacting particle system phenomenon. Helium is doing something different, which is that people are on purpose trying to mess around with these interactions, or a certain subset definitely is looking for trouble. And very interesting research question, which is how to design local, rational and Byzantine resistant mechanisms that will help you grow the network. I'm very happy to talk about this. It's still an active area. That's not it's not ready yet to sort of share and so forth, but definitely something to do. What is the right way to do proof of coverage? Byzantine resistant, rational design. But you got to feel. So that's what Helium did. So Helium is around, and we can talk. I can spend time about it. And if you search Google, you'll see plenty of things that you didn't want to see, other than technical things about it. It's a crypto company with all the pump and dump and all the flavors about that you think it might have. But it's got something going, and but it's but really to take that to an next scale, to take a decentralization is somehow there was some decentralization because the interactions were local, and that was the correct thing about it. But the rest of it, the hardware itself and the management of the entire network is all very centralized. And so decentralization is what really drives further scale and actual usage. What does decentralization mean? I'm thinking of two properties. First, it's open. That means you shouldn't have to buy a hardware from a trusted vendor at a 2x markup just because you could, which is exactly the scenario. So you really want any device, any vendor, and the economics should drive the price. Second, it should be trust-free. That means I shouldn't have to have a serial number and a password and I go register on the Helium Pay. I mean, that just doesn't sort of scale, or at least is open to misuse, which is exactly happening and live as we speak with Helium. So it should really be open to anyone, and high performers should get high returns in a way that everybody can see transparently. So that's the mechanism design aspect. So what does it take to enable this part here? That is higher performers. I did define performance here. We got some idea with coverage, right? Spread the network. So that's one performance metric, but that's only one. And the second one is more of a classic way of measuring how good a network is, which is telemetry. That is, you measure, and we can talk a little. I mean, network telemetry refers to, did I get high throughput, and how many. Basically, on your phone, you see these bars. It gives you a rough feel for how good your signal is, and you're trying to run some streaming service, and you'll see how you feel, and what throughput, what latency, what responsivity. That's the network core measurements. Traditionally, it's collected, like Verizon would collect it if Verizon is your carrier, or AT&T would collect it, and you could use that to not tell you anything. I mean, they may have, usually billing is $80 all you can eat buffet service. And so they have no incentive to give you more, but they'll do it to optimize internal performance. So that's what it's typically used for, network telemetry. But in decentralized networks, it's the whole, it's the entire core, because that's what drives the incentives and the underlying mechanisms that keep people inside the network and continuing to contribute. Which is what sort of leads to network meritocracy. So doing telemetry in a trust-free and open way is sort of core at the very heart of a decentralized wireless network. Here it's used as a optimization tool. I mean, it's still important, but it's more of an optimization. You already got it, you just want to squeeze out more out of it. But here you won't even get anywhere or grow without the underlying trust that everyone's paying, sort of getting what they should. And I want to propose this sort of a technical aspect of the talk, which is I want to propose this term bandwidth, roughly to say network performance measures. And we are looking at proof systems that establish how much a party contributes in terms of bandwidth and enables wireless bandwidth, both on the supply side, consumption side, and other network elements. So let's take a look. So here's a sort of just to say what this bandwidth is. So here's a server, google.com. UE is just, I may have some very networking terminology. Networking is rife with acronyms. Maria is smiling here. It's incredible. So you may see some of that. And if you just glaze over, that's actually even I do sometimes. But I meet enough network engineers and I live that life too much to, I'm not proud of that, but I know it. UE, but is an easy one. Is user equipment, simply a fancy way of saying your cell phone. Could be your iPad, could be a laptop, but that's roughly what it is. So your UE is trying to reach a server or the other way around. And the way you go is that you connect through the internet, the core, and this would be your hotspot. Or this is the ISP. This is your hotspot, and that connects to your device. And this part is what we would call a backhaul, all the way back to the server from your Wi-Fi router. Think of this as like a Wi-Fi router or a local base station. It's connected to the internet and eventually to a website. And this is the service itself. Like, how much did you get? Did you download 1 MB or was it 1 Mbps or what's the latency? This would be service. So these are two specific types of network bandwidth parameters. This is backhaul, and this would be service. And they're both, if you can prove exactly what the backhaul was to a third party without having to have trusted, that would be a proof of backhaul. If you can prove, if these two are pair now, it's not you, it's a pair, a hotspot and a UE, if they can pair what the service actual was, how much data or what throughput was achieved over what time scale to a third party, let alone to themselves for sure, that would be a proof of service. These are examples of proofs of bandwidth. Yeah. And this is what I'll focus, but really, if you want to think of it, there could be other things. So backhaul was here, service was here, but you could also have some kind of reputation systems. Maybe someone is saying, over time, I've given so much service over time, so I should be just having done over long periods of time, I deserve more rewards. So one can think of incentive mechanisms at an upper level. One can also think of spectrum level, maybe like a strip mall. The person who owns the real estate owns the air over that, and hence the bandwidth. In an unlicensed spectrum is owned by just whoever owns real estate. And so several real estate companies, for example, and infrastructure companies who own parking lots, strip malls, commercial estate, are all in the interest in providing spectrum. So maybe you have some ways to resell your spectrum or license it, and there's substantial interest in this. But this talk will focus on these two aspects, which is proof of backhaul and proof of service. So that's the first point, which is before you get what kind of signal you want to verify before you even got any service. If you set up a hotspot or a base station or a Wi-Fi router in your in your home or wherever you are, or in a real estate company would be wherever they own real estate, you would like to be able to prove that it's actually connected to the internet. And this would be a very basic question. How do you prove what's the backhaul for a hotspot? It's a classic question. That's the good part. So this is this part of the diagram that I had, the one side. I mean, many of us have tried this. It's a pretty standard thing. You want to know what you got, you just go to speedtest.com and you'll get something. Of course, you completely accept what they did. There was no way to. There's not even a he said, she said. It's just whatever it said, and we accept that. And yeah, so you just trust it. It's also somewhat high barrier to entry, because to enable this speedtest.com, the way it would work is that you would have powerful servers, very, very connected to your service provider. If you're through Comcast or Verizon Fiber, they're very connected directly. In fact, they're usually in partnership with these carriers. There are lots of incentive to say you're getting lots of good speed, by the way.
Comcast doesn't accept speed tests on that result.
Because I didn't give them good results.
Yes.
Maybe. So yeah, there's a substantial network telemetry is offered as a service.
Oh, a flash version? I administer our condominium.
No, it's good. I mean, yeah.
I would think they refused it.
Yeah. So in fact, many companies actually, Verizon would also say that the best 5G coverage, and there'll be a star and say we were rated by this and this company, which Verizon themselves paid. So it's a hugely self-serving network telemetry business. And I just want to say that it's, trust is just, it is what you would like to be. If it's egregiously bad, then eventually everybody will see it. And then there is some, but that's like civil war or something, like revolution. But it's not fine-grained, the mechanism design. And also it's not very open. You can't just have small servers to go check speed test. You need to be really inside the system, flood the network fully, and also have very powerful direct links to your hotspot. Right? If I go back to this figure, the speedtest.com should run like right here, or very, very close here. It can't be too far away, because then that jitter itself will clog you. Well, one way to make it open is to, and this is this one actually I'm alluding to, like some the ideas are there, where you have multiple servers which maybe partner loosely. And so they all send packets at the same time. So basically, they try to simulate as if it's one heavy duty flooding of one particular connection. So you can try to simulate multiple parties that try to do this together. And in fact, speed test itself will say we'll have 4 or 5 different, so trying to decentralize a little bit. And so there's an NSDI 21 paper very recently trying to do it at scale, but nothing to do with trust free. Okay, so there's no Byzantine resistance. So you're still trusting all these aggregators. The idea is that many of them send the packet challenges. They all come in as if it's flooding that link. So you'll measure put the measurement. So they all send back what rates they got, and you'll take some kind of some average. But there's no robustness needed here. I mean, it's just like an average will do it. So if you want some notion of a trust free, you need to basically not trust what the prover, the one that you're trying to prove what the backhaul is. You shouldn't have to trust it. You should be able to find a way that the return traffic should be, you need basically interactive. You need to find a way to interact. And if it's one-sided, you just wait for the prover to tell you, then they can say whatever they want. So you need to have this interaction to help you tie down the prover to what they were saying. And you can use some basic internet measurement tools. PathCare will do it. IPerf was related to speed test, but PathCare will tell you, which is you'll send 2 packets. One would terminate here, you drop it, and you send back the return time. The second will terminate here, that will send its return time. And this is trusted though. The ISP is said to be trusted. So this is the one that presumably wants to prove how much it has. And so you take the difference between them. And you send a large enough packet so that you sort of flooded the network. It's fully queued up, and so you don't see any effects of other packets coming in the cross traffic. So this would be using PathCare, but it's not. But as you can see, there is a delay here, and you have to average out the delay. And if you are doing long distance, then the delay itself will dominate. The jitter in the delay itself, the measurements are large enough, so you can't really measure high backhauls. So dispersion is not the best. So you can try to put this. So it's good. It has some trust-free aspects to it because you don't have to trust the prover. But it's still not open. I mean, you still need a strong connection. You can't be far away. So you can put the 2 ideas together, perhaps, right? Aggregation help you make it a bit more open. There's interactivity where the prover sends the timing signal back, either through an explicit signal in UDP, or TCP will also automatically send the feedback signals. That's a bit lower level networking detail. And you can try to put the 2 things together and say, maybe, this covered the openness, this covered trust free, and you put them. But, we know in security, you try to put these things together, new attacks open up. And for example, some of the challengers could collude with the prover in various ways. And in particular, for example, corrupted challengers can just not even send their packet. Or so, for example, if you're taking the average in some way, then they can just hold you up. Or they could rush. In other words, they never actually send the packet. They have some side channel through which they'll send it very fast. And then they can pretend they got it whatever time they wanted. So it could rush it. So clearly, if all of the challengers are colluding, then forget it. That's not going to happen. But presumably, hopefully, a fraction collude. And you have a more Byzantine resistant interaction scheme. And what would this scheme, what would it involve? First, it should have some kind of unforgeable packets. That means the challenger should have some signatures. So that's very basic cryptographic primitive we'll have. You also, when you want to take averages from different measurements, you want to do some kind of a robust hypothesis test. Median would do better than average, right? Median would be robust. And also you want to, just for efficiency, you don't want to go back and send large packets. That could also mess with the measurement, but also just from a practical efficiency point of view, you want to have some very short witnesses. So the feedback is fast and lightweight. So here's a proof of backhaul protocol that has a Byzantine resistance property. And we'll say what the property is and what we built. So you have multiple challenges. The aggregation part is there. And they send, say, signed traffic. So it's not forgeable. So you know who they are. Presumably, these challengers have been picked at random. That's not grindable. So that means it's some external source of randomness. And there's a reason to do it in a blockchain because there is inherent sources of randomness in a blockchain that can be used to drive these randomness. And then you have a return time. And you want to make sure that this is, fault tolerant. That is, the return back to these challengers or to a verifier is something cryptographically secure. It ties all the measurements. It can't say one to here, one to there. So you tie them all together, and the hash will do it. However, a hash aggregator is even more efficient. So you'll do something like a Merkle root. But each challenger themselves should be able to locally verify that my packet was actually received and recorded. So then you will need some kind of a proof just locally. And finally, you want the verifier will have to take some appropriate, robust, Byzantine resistant measurement. So here's the graphic. So you send the traffic, right? The packets are all coming in. So you send a lot of packets. So you wait until the packets queue up fully. So the entire queue is filled up, it's fully buffered up. And then you send the packets over. The prover, which is this hotspot, will try to compute the hashes of the different packets. It will also aggregate them through, let's say, a Merkle tree. And that Merkle root is reported to a verifier. It's natural to implement it on a blockchain for a variety of reasons that I was just alluding to, but it's a core basic, it's what I call a Web 3.0 primitive that can be stitched together inside a platform like blockchain. But the proof itself, which is the packet indices and Merkle proof, are sent to the individual challengers who go and report these proofs to the blockchain. So the blockchain doesn't have to trust any of these, but these proofs, the local proofs, and the Merkle root is enough to sort of verify, enough subject to how many, and then it can take these measurements and take a robust, let's say, median as the median measurement. In practice, of course, there will be network jitter, there will be synchronization errors, there's some computational overhead which affects networking because queuing delay and computation delay, serialization, deserialization, and just compute will also provide delays to your backhaul. So these are all very practical things. But doing it lightweight lets you open. And if I had some time, I'll give a demo, like a global demo that we built over a large scale. There's a, I think, 4-minute video at the end. And so one can have a sort of a formal security, which basically says that if you have F of the challengers faulty out of the total N, then that affects the accuracy of measurement. First of all, you cannot inflate. So that's the good part. That was really what is usually a problem where the prover will just inflate saying that I have, 1 Gbps. You can say whatever you would like to get the highest reward. So that will not happen, but you could be, but an attacker could try to bring you down by messing with this protocol. And that is sort of bounded by this. And this is only a scheme. So here you see the threshold is 1/3, but there's nothing that fundamental about it. You can get to half with somewhat more sophisticated schemes. Involving coding, but we can do that offline. Those schemes also, I would say, have a little bit more heavy implementation. So it's not clear where the trade-off is. Any questions at all on this? So this gives you an idea of what I meant by building the basic building blocks of this fabric that ties decentralized network together. The first primitive we saw was proof of backhaul. How much connection to the internet do I have? Yes, Maria.
Yeah, that's super interesting. I was wondering, like those metrics are actually dynamic. So you talk about RDT. RDT can change really fast, especially like in congestion issues or so. At what granularity, how fast can this run? Like, how can we make sure that?
Yeah, so I think we just sent a paper to NSTI. So we can go all the details. So basically, if it's TCP/IP links, you have substantial issues, especially you hit into congestion control. So we did a lot of experiments with UDP. We also did some experiments with some very more specific, like Zoom traffic or Google Meet traffic. And wherever you have a little bit more control over the kind of traffic you get and you can send it back, the finer the measurement. This is true in general in telemetry. And it's the same effect here, which is the closer you can be to flood that packet and not have cross traffic. So we did several experiments around it.
But isn't this public internet? No.
It would be public internet, yes. But your challengers. Okay, let me give an example. Our challengers are all running on AWS.
I see. So you're trying to measure the AWS links then.
No, the AWS will let you access the hotspot faster. So let me go back to this. We can look at this figure, right? So the challengers, wherever the challenger is, it's connected to the service provider through your AWS.
So you're taking the ISP only, the provider.
That's the only one we are really in. Backhaul is all about the ISP. Is how much this this connection is.
Okay, so you're trying to flood it.
This is the
extent-
backhaul
okay,
bandwidth.
got it.
I want to flood this particular
Mhm.
one, and I want to flood it as quickly as possible.
Mhm, mhm.
But you're right in the sense that if you're trying to do it through the internet, then there is congestion and the internet itself will start changing that. So you don't want this link from the challenger to this ISP to be the bottleneck. Basically, that's what you want to avoid.
Got you, but like in general, you seem to focus more on like what is there rather than the small dynamic changes that can happen over time. Like you want to know how the ISP is provisioned, and in general, what is the performance rather than what is the performance in a millisecond.
No, backhaul, we are not interested in millisecond. This one would be service quality. We might be interested in latency and some very specific performances, but backhaul is an average quantity. I mean, I'm not talking about the mechanism design, but in general, you probably don't want mechanism designs that change to fluctuate too much over backhaul. You want some reasonable quality. Most of all, you don't want people to put in their basement, never do anything and claim it's there. I mean, that's the real issue, which happens with hotspots in helium all the time.
Yeah, I mean, coverage is 4-dimensional, whereas all your diagrams are 2-dimensional. But yeah, coverage.
While this
changes.
is being discussed, could we go back to the figure with the Merkle root and the just the showing the flow of how the challenge is issued? Okay, yeah, thank you. I just want to look at it while this is going on.
So this was a basic primitive that we built. So proof of backhaul. It's just a connection. This link, this is the backhaul link. Let me give some idea for what the other side would look like. Service, I think.
Don't you need something in there to the sort of right end of the okay, sorry. So I understand the Merkle arrangement here, but shouldn't there be something that shows that the hotspot actually like the path made it all the way there? So okay, so every one of these, you're like adding another node to your Merkle tree, and you're retaking. By the time it gets all the way to the end, now you have the root over everything.
No, not Sarah. So this is it Sarah?
Yeah.
Yeah, we can't see you, but so the great. I just want to highlight one thing is that this aggregation is just for efficiency sakes. You know that's why you don't. Okay, that's just purely efficiency. Just to be clear. That's why you don't do it. But from just a practical perspective, these packets are done one at a time. So you can think of lots of packets. You want to take some average over it. And I want to say the average should be averaged over both K. That average can be done over K, but you do a robust average over N. So that's these hashes are done just so that you don't have very detailed or every packet by packet feedback.
So the 1 ... K in the bottom right, is that the like what okay, yeah.
So these are the packets. So this color here, right? This cream color are all packets sent by the first challenger. The signatures on that. So the signatures.
Are these the packets containing? So there's a message. The server signs the message, and it sends presumably the message and the signature. And then what does the hotspot actually do with that?
What does the hotspot do? Well, hotspot does in this case 2 things. First, it it puts the packets together, computes the hash individually for each challenger, but it also aligns these and aggregates the hash as a Merkle root and sends them to the verifier. So I can
But the 1 ... K thing down there was just the packets of the message and the signature that was sent by each server.
they are sent over to individual challengers so they can have local verification that indeed my packets were received. And
see.
that's what recorded. But the
Okay.
very, but these guys, some of them could be colluding with the prover.
Right.
So that's not enough by itself.
Okay, thank you.
Thank you. You know what? I think, I wanted to spend some time about the other side, which is how much service did you give? And I'll try to say what the challenges are and what kind of primitives it takes and what ideas, just to give a feel for the kind of area this is, because this is an interdisciplinary area. You have networking, quite core networking topics, at the same time, security issues and incentive mechanism design. So it's sort of an intersection of all these three. So traditionally, billing is definitely centralized. I mean, Verizon gives you a bill and that's, I just pay. I mean, that's that. So measurement and billing are all together. And no wonder they'll just say, yeah, there's no incentive to, yeah. And yeah, this is very networking slide. So where they are in different components of the network stack, basically they're all out in a very far away from both the core and the radio. Measurements are all here, but yet somehow all measurements and billing are happening way out. These are all different blocks of the network stack. And that's just given to the base station. This is a very classical view. And there are two parts if you really want to decentralize this and also make it trust-free. First is that you have to make sure that payment and service are guaranteed. That is, the supplier could, the consumer can just pay the money, but I never got the service. Likewise, I got the service, but then the consumer can say, I never got anything. I mean, this is like a very basic chicken and egg issue here, right there. And there's nothing to do even with, at some level, the networking. The networking is an infinitely divisible good. So there's something very correct about that particular good as opposed to just getting a Tesla one time, right? A Tesla was there one time, I think they were taking Bitcoin for Tesla. So that's my illusion. But it's just one time. Networking is packets come and there is an infinitely divisible, you add data. So there's an additivity aspect to this. The second part is that how do you verify what was the actual service done? So there's payment aspect and then there is the measurement aspect. So you need to solve both of these and you need to bring some combination of networking protocols or methods together with the right crypto resistance or security, Byzantine resistance. First is that you need a payment mechanism that has trust-free escrow mechanisms where there is a commit, that is, I put in something in escrow, verify, both sides agree on that, and then release. And this is a core building block of several, especially Bitcoin scaling solutions. They're called payment channels. And it's a core building block in blockchains. You could say it's a primitive. It's a Web 3.0 primitive. And the second part, this is where networking, which is that you need both sides to measure. And they have to commit to their measurement. Only one side measures is no way to ever have trust. You need to have both side measurements and find a way to resolve if there are any disagreements. And so you have to put the ideas together now. So these are the basic primitives again. So you have the escrows, which are put inside smart contracts. Again, a very core Web 3.0 or a blockchain primitive. And you have state channels and micropayments that are also core primitives that keep where the channel is, how much has been paid, and what has been left in the account. And how these states get updated all depend upon the measurements. And the key is that both sides have to measure. The service provider and the consumer, the user, both sides have to measure it. And yeah, so we can look at the architecture. And like I said, we can go over this in detail. But I wanted to show a short video of a demo of such a wireless network built at scale. So this demo is to build a certain application. It's called an ECN, or we call it an ECN. We all know EC2, Elastic Cloud Compute, where you just go online and buy compute. This is a similar vision where you can go online and buy networking. I'm here, I need this much data, this much coverage for this much amount of time. So I should be able to book a network slice as opposed to some course or memory. So it's called an ECN marketplace. And this is the proof of concept. It's running live in Bangalore. We have, then this is the entrepreneurial aspect. So this effort took a lot more than university resources. So, it's running live in Bangalore, is in South India. So we have about 5 megahertz of spectrum from the Department of Telecom in India, with experimental license. So it's a live over the air running network where you can buy spectrum, buy bandwidth and buy networking online. So the interface would be exactly like EC2, and you have an orchestrator that would do this. So it's a trust-free network. It would be, it's a piece of software that we run, but it's a trust-free piece of software. I mean, we are running it right now, but it's open, trust-free software, can be audited by anyone. That connects apps on one end. So who is the purchaser of buying networking on the fly? This would be all the modern applications, which would be the metaverse and the cars and smart home devices. I wanted to spend a few minutes with this video, if we can.
Communicating over band 40. The system runs on cloud and has a global view of the network state, which can be visualized through the monitoring dashboard. The dashboard shown here gives an overview of the entire ecosystem. The map shows the density of SLAs deployed across the United States. On the right, you can see carrier funds in tokens. When data is consumed by the users, the funds increase through micropayments.
Let's demonstrate how a user will book an instance. The booking process requires the user to go to the booking portal and enter information about the UE. Once you come to our ECM Marketplace website, you will be able to see the offerings. There are multiple network instances available in each region. If you select the instances in Illinois, you can see that there's one for interactive gaming, which supports 3 Mbps, and there's another one for voice, which supports 1 Mbps. If you look under the hood, you'll be able to see that this one, for voice, provides a proof of bandwidth every 2 megabytes. Let's book this slice. When you press Book Me and go to the slice booking page, you will see all the details of this slice. You can enter the date for which the slice is valid, you can enter the total data usage, and you can enter the phone number where you would like to book the slice. After completing the details, you can press Book Now, which will take you to a payment confirmation page, where you can confirm the payment in tokens and the booking will be complete.
Once the booking is made, Kaleidoscope will manage network delivery as per the SLA requirements and automate trustless token settlement for the services provided. Kaleidoscope obtains data usage measurements from both the base station and the user. The user makes payments in smaller units called micropayments and not for the whole booking at once, which enables a proof of bandwidth delivered. In the remaining part of the demo, we will see the state of the dashboard after the booking is made and see live updates on the dashboard as data is consumed by the user. We made a booking for a slice in Illinois earlier and another one for California with higher throughput. On this dashboard, these bookings can be seen. If you go down, you can see that the 2 devices corresponding to the 2 bookings appear here, each with full funds remaining since they have not started using the data. These devices are 2 laptops, each using a 4G dongle and connected over the air to a 4G base station. We will play 2 video streams on the 2 slices, a low resolution stream on the Illinois 1 Mbps slice and a high resolution stream on the California 5 Mbps slice. We have now switched on the 2 UEs. On the left is the Illinois UE with 1 Mbps and on the right is the California UE with 5 Mbps. As you can see, the UEs have started streaming their videos. You can see that the remaining credits are reducing for the UEs as they use more data. With data consumption, UEs make payments and tokens are moved from UEs accounts to the carrier's accounts. This information about the consumption of data is coming to the Kaleidoscope bridge from the base station and the core, which are delivering data to the UE. Credits are consumed in units determined by the micropayment interval that we saw during the booking. At the same time, you can also see that the throughputs as measured by the UE are available to the Kaleidoscope bridge. These 2-sided measurements allow us to build a trust system where the UE pays for the data it has consumed and nothing more.
Yeah, so I'd like to thank my collaborators, many of them at Kaleidoscope, but also academia. Sachin is here at Stanford, Sarat is from Stanford, Sriram is from University of Washington. Thank you.